Hello everyone, this is Lin Yang. I'm going to talk about our paper about settling the horizon dependence of sample complexity in reinforcement learning. So this work is joint work with Yuanzhi and Ruosong Wang from CMU. Myself is the assistant professor at UCLA. Okay, so let's get started. So probably in this community of FOCS, right? So most of you are not familiar with what is reinforcement learning. Okay, so let me give it a very brief introduction of what is reinforcement learning. So basically, I guess some of you have already heard about a multi-embedded problem, right? So reinforcement learning can be understood as the extension of an MAB problem. Basically, you can understand that there is an agent who wants to interact with the unknown environment only through trial and errors. So compared to a multi-embedded problem, as you can see here, it's very similar. So there is an agent who can take interactions with some unknown environment and receive feedbacks, and later on want to optimize this sequence of actions. And the difference is that the agent now needs to take a sequence of actions rather than only one action. For instance, here, right? So the agents need to take action A1 to AH. And then after each action is taken, the environment also gives two kind of feedbacks. The first one is a state, the second one is a reward, which is a scalar. Okay, so after this edge steps, which we call it the horizon. Okay, so this whole procedure is called an episode. Okay, so the agent needs to take an episode of interactions with the environment. After that, receive a bunch of feedbacks. Remember that these feedbacks are depending on the state, right? So at a different state, you might get a different feedbacks. Okay, so that's the subtle and different part with my MAB problem. And later on, the agent wants to maximize the expected cumulative reward. It's a sum of all the reward that matters. Like any single reward doesn't matter at all. For instance, if you want to maximize the whole sum, you may want to minimize the first reward and you want to get the best rewards of the following steps, right? Because of the state transition. So the long-term effect matters here rather than the single greedy kind of solution that's usually doesn't matter. And that's also the core difference between reinforcement learning and other type of machine learning problems. Okay. So in order to model this kind of thing, we usually introduce the so-called Markov decision process that basically models the environment as a finite state system. So like this graph diagram, I said at each state, you can take actions from some finite set. Once an action is taken and the environment is performing some state transition to another state with some probability, that's a PHSA at a different step. But this transition probability is usually not known to the agent. And at the same time, the agent can receive some scalar reward in between 0 and 1. Okay, that's a scalar reward. Okay. As I said before, right, there is a horizon parameter edge. So the agent needs to take an episode of data and that like often as edge. Okay. And in order to model this agent solution to this problem, we use the so-called policy. Okay, policy is a function that maps the state and the time. So like a horizon edge, right, in between, it's a different time to a distribution of on this the action space, right? So the agent might take random actions. And then, so the agent take this edge steps, right, receive a sequence of reward, and this state transition is called a trajectory, receive this trajectory of rewards, right? And then the sum of the thing, right, is take expectation is defined to be the so-called value function of this policy pi. And then the goal of the agent is to maximize the value by applying the correct policy. Okay. Of course, in the learning setting, because probability transition is unknown, right? So we usually allow a bit the suboptimality. For instance, we put epsilon here, we want to get a policy that is epsilon optimal with high probability. Okay. All right, I hope that is clear for this problem. And actually, a long line of research and like studying this problem, in particular, that right now there's already a very mature recipe of solving this problem. It's actually coming from MAB problem as well. It's called exploration and exploitation. You need to balance these two in a good way and to get a good policy. So the rough procedure is like this, right? In the beginning, we know nothing about the system. We're going to learn that from scratch. Basically, we're going to pick some arbitrary policy. And then because the policy is arbitrary, we're going to play that policy in order to get sort of certain understanding of the environment, right? That's the so-called exploration step. You just play that an action to collect a bunch of data points. The data is a bunch of trajectories of interactions, okay? Once you get the data set, you want to do the so-called exploitation step. Basically, you want to use the data set to solve for a good policy, to get a new policy, and then continue this procedure. So basically, each iteration is kind of like you collect a new trajectory of data or a new episode of data, right? So we care about the number of iterations of such kind of a procedure, okay? All right, so there are a lot of algorithms already proposing either upper bounds and lower bounds for this problem. For instance, here, so I'm highlighting the dependence of the horizon, okay? So here, the horizon dependence is using the assumption that the reward is uniformly upper bounded between 0 and 1, like I said before. But this thing is only a scalar factor, right? So because you're assuming such, the sum of rewards, it can be at most h for an episode, right? So that's actually introducing a scaling factor. Using that kind of a scaling thing, you get an optimal dependence. It should be polynomial in h, and it should be h to the 3 dependence here, okay? So there are a lot of other results as well. I haven't included them here. So if people are interested, could look at papers who cite those papers, okay? All right, so that's the current situation of this problem, right? So as you can see, as I mentioned, right, so the core problem in reinforcement learning is really to understand the dependence of horizon. But like I said here, in all those papers, they care about this horizon dependence by using the scaling that reward is bounded in between 0 and 1, which might not fair in order to study the horizon dependence. For instance, let's see, consider multiple bounded problem, right? So for multiple unbounded problem, you plan an action, so you're gonna get a reward which is bounded in between 0 and 1. You can assume that, okay? But for reinforcement learning, so an action in MAB is corresponding to a trajectory, like a trajectory of data in reinforcement learning. So now look, so the reinforcement learning, the sum of all the rewards, right, blows up by a factor of h, right? So that may not be good enough for us to compare the complexity or for us to study the complexity of reinforcement learning and the previous, let's see, MIB setting or usual learning setting, right? So in order to handle this thing, we use this file setup. Basically, we say that we get a bounded total assumption. Instead of assuming that each reward at each step is upper bounded, we just put the assumption that the sum of all the rewards is upper bounded. So now, because of this assumption, right, then now you consider a trajectory of interactions, you receive a trajectory of rewards. The sum of them is upper bounded, even though that's a random number, right? But now it is comparable with the MAB setting, okay? So now it's a fair comparison. You can introduce a fair comparison between MAB and RL, okay? So the previous solutions, right, in the previous slides, right, they consider this uniformly bounded solution. So you can also convert that thing in our setting, but now it gives a very restricted assumption, right? It's 1 over h. Basically, in that sense, right, the previous assumption is not, it introduced more constraint on the reward. This assumption will introduce less constraint on the reward, okay? All right. Yeah, so now let's recap again. So what is our goal? Our goal is, of course, wants to understand how many interactions you need to take to interact with the system and to get a order 1 optimal policy, right? So in particular for this kind of what the bounded total assumption, so that actually this problem is first proposed by John Agor in 2018 code. They conjecturing that actually omega h lower bound should be there because like I said, right? So edge is fundamental in reinforcement learning problems. So maybe you have to have some dependence on edge and deconjecturing a omega edge and over one. Unfortunately, this is not true actually in 2020. So me, Simon, me, Ruosong, Wang, and Sham Kakadi, we found that actually this is not true. So we are proposing an algorithm so that refutes this conjecture and showing that polylog dependence is sufficient in the sense that you do not need to interact with the system for edge episode. You just interact with the system for polylog edge episode. That it's sufficient for you to get a good policy. And so, of course, there are a lot of other follow-ups for this kind of results. Okay, so they trying to improve the time complexity and other SLAT efficiencies, etc. But they all have this polylog dependence. Okay, what's new here? So actually in this paper, we show that you only need 1 episodes in order to get a good policy, okay? So here it is surprising in the sense that it is tied in edge, right? So this number of episodes has no dependence on edge at all. And so it actually gives us the claim that the no horizon, short horizon problem has the same complexity. I'm putting caution mark here because we are actually hiding a horizon dependence in the episode. Remember that you collect an episode, right? So the episode already contains edge samples. So that's the only dependence of edge in our algorithms. There are no other edge dependence. That's actually the surprising part. Of course, this algorithm still has a very bad dependence on the state and action pairs. For instance, it's exponentially depending on state action pairs, which we leave as an open question to resolve for the future researchers. Okay, I mean, this actually refutes our own conjecture in our 2020 paper, saying that, okay, maybe at that time we thought that polylog edge dependence is necessary, but turns out it's not. Okay, all right. So in order to tell you more details about the algorithm, I would like to tell you a simple algorithm that we have in the previous paper that we get the log edge dependence. Actually, before that, I want to tell you something more like how people got the similar things in their results. Actually, most of them are using the so-called dynamic programming method. In fact, if you are given MDP, solve it the best way perhaps is the dynamic programming method, right? You can understand that MDP is a stochastic path search algorithm, right? However, if you do so, you're going to have a lot of dependence issues in terms of the random samples you collected. So that gives you polylog edge dependence. Probably this might be the name for a dynamic programming method-based method. Okay. Of course, I want to tell you how we get this thing. In fact, we are using a very simple idea that is based on this Monte Carlo estimation policies. So let's now suppose we're not considering the optimization problem of finding the best policy. We only want to find the value of a given policy. How are we going to do that? In fact, it's easy, right? You just play this policy to collect the trajectories and collect a bunch of them, and then do an average that gives you a value estimator. And remember that our sum of rewards is upper bounded by 1, and the sum of the collected rewards is a random variable, but with variance upper bounded by order 1, right, per episode. In that sense, you only need order 1 episodes in order to get a good estimator for the mean of the value functions. Okay, that's good. However, if you want to use this to estimate the best policy, you need to search for the best policy, right? You need to run it for a lot of policies. The number of policies can be exponential in terms of the horizon, and that can doom your estimation or optimization procedure. So in order to solve this problem, we actually come up with the sample reuse problem. Sample reuse property is in that actually you can reuse the samples collected from previous policies. And because of so, we see that if you want to estimate n policies for very big n, you only need polylog n trajectory of samples because you are reusing the samples, right? That's actually not enough because if you want to find the optimal policy, you need to do so for every policy, but the total number of policies is going to be exponential in edge. So to solve this, we find a subset of policies already suffices for us to do this kind of a search procedure. Basically, we find a policy cover that covers a policy that is nearly optimal. So the size of such policy cover is edge to the SA instead of exponential in edge. So with the union bound of this thing, you can have a polylog edge dependence, right? But it's hard to get rid of this polylog edge dependence after this step, okay? So how we resolve this problem in this paper? So we use some new ideas. One of the major ideas is the so-called stationary policy. So look, all the difficulties of this policy cover comes from the edge factor over the power, right? And like that. So, but if we consider stationary policies, remember the stationary policy, what is that? Let's record that, okay? Stationary policy is a policy that doesn't depend on time. So like at every state, it always play the same policy. So there are not that many stationary policies. In fact, it's A to the S, right? Because there's no edge factor there. So if we can use these stationary policies to do something, that would be super, right? However, it's usually not possible because you can always show that in an infinite horizon problem, stationary policies can be very bad. And because of so, we cannot use that as a policy cover because it may not contain a good policy. However, we can show that if you use this set of policies, you can actually estimate the probability matrix up to some certain high accuracy that's good for us. So in order to use this kind of thing, we really need a better perturbation bound to understand the probability matrix estimated using this way. That's our first contribution, actually. That's the so-called perturbation lemma. So the perturbation lemma says something like this. So if you use the policies to collect the samples and estimate the probability matrix afterwards, so you're gonna get some arrow bond like this. This is coming up from this Bernstein bond. It's actually a very easy bond, right? So you just do simple counting and then estimate the probability and it gives you arrow bond, okay? So our perturbation lemma says that this arrow bond is actually sufficient for you to get a good policy. So it doesn't make sense to look at this equation, but if you look at the previous method actually tells you that if you want to use such kind of estimator to get a good policy, that will blow up the error by a square root edge factor. This is so-called error compounding effect in dynamic programming, okay? That gives a huge error factor. If you use previous bond, this eventually leads to a poly edge sample bond, which is not good. But if you use our perturbation lemma, that completely get rid of this effect, okay? All right, what's next? So like I said before, right, so we really want to argue that the stationary policy is good for us to estimate the probability transition matrix. Because of time and time limit, I cannot tell you much details about that. In fact, we are using infinite horizon MDP as a proxy and show that there are certain relationship between stationary policies and the finite horizon Markov decision process, even though these policies are not good in terms of value, but they can be good in terms of estimating the probability transition matrix, in the sense that if there exists a non-stationary policy achieving some state with high probability, we can use the stationary policy to get another policy to reach the same state with roughly similar probability up to some constant factors, okay? Of course, this constant is really exponential in terms of the number of states. That's where the exponential factor comes up. All right, so that's the second factor. And with this argument, we can show that stationary policies, or at least some variants of stationary policy, can be used to estimate the probability transition matrix. Of course, I'm hiding a lot of subtleties. For instance, we have to use a quantile instead of the mean to estimate the probability transition matrix. And then we have to concatenate two stationary policies instead of using one stationary policies to collect the samples. And then lastly, we show that in order to get a good policy, we cannot directly solve the MDP, empirical FDP. We have to do some sort of pessimistic planning in order to get a good policy. Like all these subtleties, they all come together and eventually gives us a way to solve this problem and get rid of this polylog edge factor. All right, in summary, so we solve this problem, right? The reinforcement learning problem under this bounded top reward assumption, sum of rewards are bounded by 1. So we show that in such assumption, there's no dependence of sample complexity in terms of the edge. So we provide some technical contributions including perturbation-lemma, approximation-lemma of station policies, limit of independent interests. So we leave an open question about the better dependence of state and action pairs. All right, that's everything. Thank you so much.